We're now going to use the multiplication rule for independent events. Here's what the multiplication rule for independent events states. If E and F are independent events, then the probability of E and F equals the probability of E times the probability of F. So when you see the word and, think multiplication. When you see the word or, think addition. And multiplication. Or addition. All right, let's continue with our dismal example of people surviving the year. The probability that a randomly selected female aged 60 years old will survive the year is 99.186%, according to the National Vital Statistics Report. What is the probability that 2 randomly selected 60-year-old females will survive the year? So here is essentially what we have. Probability first survives and second survives. We need to ask ourselves whether or not these two events are independent. In other words, does the survival of the first woman have anything at all to do with the survival of the second woman? No. The reason that we say no to that question is because the women were randomly selected. We have no reason to believe that these two women are related in any fashion. And therefore we can say the probability first survives and second survives is the probability the first survives times the probability the second survives. What is the probability the first female survives? .99186. And what's the probability the second survives? Also .99186. And if we find that product, what do we get?
0.9837.
0.9837. So essentially, if we randomly selected 100 pairs of women, we would expect about 98 times that both those women would survive. 2 of the times, at least one of the women would not survive. Does the interpretation make sense? Because I really want you to, over and over again, when you're doing these problems, state what these results mean. Because getting the results isn't all that complicated. It's explaining what these results mean, because we're going to be using probabilities for the rest of the semester, and understanding how to interpret probabilities will make your lives a lot easier later on in the course. Okay, so again, if we were to pick 100 pair of randomly selected women, we would expect about 98 of the times both women to survive the year. 2 of the times, at least one of the women will not survive the year. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year that it is purchased. Unless you count using it as a clothes hanger counts. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? Now, you have to think about this. To make a valid warranty claim, 2 things must happen. 1, that customer would have to have bought a defective piece of exercise equipment. 2, the customer would actually have to use the exercise equipment. Agree? And so what we're asking here is the probability that the equipment is defective and the equipment was actually used. Now, ask yourself this. Does the probability that a customer purchases a defective piece of equipment have anything to do with whether or not the customer actually uses the equipment? In other words, does a company intentionally try and sell defective pieces of equipment to those folks that they suspect aren't going to use it?
No.
No, they don't. That'd be a pretty swift marketing plan, but they don't do that. And so it's reasonable to assume that the defectiveness of the equipment is independent of whether or not the equipment is used. Therefore, I can use the multiplication rule for independent events. And what is the probability that the equipment is defective?
0.1.
0.1, 10%. Agree? What is the probability the equipment is used? 0.3. What's 0.1 times 0.3? 0.03. So if I sell this equipment to 100 different customers, I really only expect about 3 warranty claims. This is interesting but gloomy at the same time. Who here recently graduated from high school? How many were in your graduating class, would you say?
300.
300? Okay. Let's say that the probability, how old, you were 18 when you graduated from high school? Let's say that the probability that an 18-year-old survives to be 19 now, a 60-year-old female is 0.99816 or something like that. Isn't that what I had in the problem? 0.99816? 186. So you got to figure an 18-year-old is going to have higher probability than that. 0.999, would you say? Seems reasonable enough. I mean, we could look it up to find out exactly, but so if we wanted to know the probability all 300 from a graduating class survive to be 19, or survive at least 1 year after graduation, we could do this if we're willing to make a somewhat, maybe it could be argued, unreasonable assumption that the events are independent, because obviously these students probably hang out with each other and do a lot of the same things with each other. Namely, one of the most reckless things that 18-year-olds do is driving cars together, right? But nonetheless, if we are willing to make the assumption that these 300 students the survival of them is independent, that would basically mean we want the probability the first survives, I'll just use S for survives, and the second survives, and all the way down to the 300th survives. Now, if we're willing to make the assumption of independence, that would mean the probability the first survives times the probability the second survives times all the way down to the probability the 300th survives. The probability the first survives is 0.999. The probability the second survives is 0.999. And the probability the 300th survives is also 0.999. So essentially we're multiplying 0.999 times itself 300 times. Agree? Which is equivalent to taking 0.999 and raising it to the 300th power. So what is 0.999 to the 300th power?
0.74,
0.
0.74? 0. Okay. So if we looked at 100 different high schools with a graduating class of 300, we would expect about 74 of those high schools to have all 300 students survive the year. Which means that there are about 26 of those high schools that don't have all the students surviving the year. And what I want you to get out of this is that while it's obviously a tragedy that certain 18-year-olds don't survive till a year after graduation, it unfortunately is not all that unusual.
74 don't survive, or 74?
74 out of the 100 have all 300 surviving the year. So that means that 26 of those high schools have students.
We're saying 74 high schools? Or
Right. When we do interpretation, it's a relative frequency approach. So 70.74 could be thought of as 74 out of 100. Agree? So basically what I'm saying is if we looked at 100 different high schools with a graduating class of 300,
yeah,
about 74 of those high schools would have all 300 students survive. Which means that about 26 of the high schools will not have all 300 students surviving, or put another way, at least one of them does not survive.